Thank you for your interest in Bharat AI SoC Student Challenge. This initiative, driven by ARM and ARM Education, aims to support skill development in India by encouraging students to tackle industry relevant problems and devise innovative and impactful solutions. We are proud to partner with Mighty C2S program as well as collaborate closely with IT Delhi, our lead academic institution in this endeavor. I extend my gratitude to Ministry of Electronics and IT as well as IT Delhi for their support in this exciting initiative. Good luck to all the participating teams.
Hi everyone, I'm Nish working as a research scholar at IITD in the field of safety enhanced cache architectures. I'm one of the program assistants for ARM Bharat AI SoC Student Challenge and I will be explaining problem statement 5. This problem is on real-time object detection using hardware accelerated CNN on Xilinx Zynq FPGA with ARM processor. The objective of this problem is to design and implement a hardware accelerated CNN inference system. For this, you will be using Xilinx Zynq SoC. The FPGA fabric will be used to achieve real-time object detection. You will have to quantitatively demonstrate performance improvements over a CPU-only solution. The prime focus of this problem is on accelerating edge AI workloads. The CNN implementation will be handled on a Xilinx Zynq SoC. This integrates an ARM processor along with the FPGA fabric. This is essentially a hardware-software co-design problem wherein you need to appropriately divide and partition the functionalities in between the ARM core and the FPGA unit. As an example, the ARM core can be used for image capturing, pre-processing, control, and post-processing tasks, whereas the FPGA can act as an accelerator for compute-intensive CNN operations, such as convolution, activation, and pooling. You can use Vitis HLS, Vivado, or any other suitable development framework for this problem. You can also use Pink and Fin compiler as starting points. The Git link is provided in this slide. The final system should be able to perform real-time inference, and you should be able to demonstrate comparison against a software-only solution. The overall system can be envisioned as a combination of a camera unit, the ARM core acting as the preprocessor, and the FPGA. The camera unit comprises of a USB or an onboard camera, which can take live feed as the input. The ARM core can then be used for camera configuration and receiving the raw images. Based on the accelerator requirements, the ARM core can also be used for resizing, reformatting, and packing of the camera data to make it more appropriate for the accelerator. The FPGA executes the convolution layers and pooling and sends back the data to the ARM core. The ARM core can then handle the post-processing task and display the results on a display console. In terms of hardware requirements, you will require a Xilinx Zynq-based development board. This can be either of Zynq 7000, ZCU104, or a Z board. The input image dataset should be able to support both the camera input as well as stored image dataset. For the camera input, you can use either a USB camera or an onboard camera if the board supports that. The output should be a bounding box with the classification on a display output. You can also add a serial console as an optional output. The display unit is a mandatory thing and the serial console can be an optional addition. In terms of software requirements, your datasets must include but should not be limited to Coco, and Pascal VO classes. You can use lightweight CNN models such as TinyYOLO and MobileNet. You can also add your add other models to your solution. For CNN accelerator implementation, you can use Vitis HLS, Vivado, or any other suitable framework. For the design of various hardware modules, you can use Verilog or HLS C++ or any other HLS. For hardware software co-design, you can use Vitis or SDSoC. For image processing, you can use OpenCV. For control logic and overall integration of the solution, you can use C++ or Python. We have some certain performance metrics which are expected to be met. These include a real-time or a near real-time inference on the embedded hardware. A minimum of 2x speed up as compared to software-only CNN execution on ARM CPU is expected. Besides these, there are significant improvements expected in the latency, throughput, and power efficiency. A good FPGA hardware resource utilization is expected in terms of LUTs, VRAM, and DSP usage. Going through the deliverables, the main deliverable is a Git repo. This Git repo must be public, which will ensure a streamlined evaluation. The Git repo must comprise of all these files related to the working FPGA accelerated prototype, the entire development code. This should include all the Verilog modules which are used in the project. The documentation is a key part of deliverables. The documentation should comprise of system architectures and design decisions, the diagrams and code snippets, performance analysis, and comparison. The key design decisions and the system architecture must be clearly and eh, well explained in the documentation. The block diagrams, the internal diagrams, the code snippets, etc. should be part of the documentation. The documentation should have a good performance analysis in terms of accuracy, latency, throughput, resource usage, and power consumption. It should also comprise of comparison in between CPU-only solution and your solution. Besides these, there should be a live or recorded demo showing FPS or latency as well as prediction confidence. We will evaluate the submissions based on certain metrics. We will use a custom dataset and the evaluation will be based on three key aspects which are completeness, performance, and novelty. First of all, the solution must be complete with all the deliverables in place. The performance is a key aspect and we will evaluate the system performance based on four metrics. These are accuracy, latency, resource utilization, and power consumption. The accuracy will be measured in terms of average precision based on intersection over union. IOU is a ratio of area of overlap and the area of union. These are the areas of the detected bounding box and the ground truth. The IOU is expected to be higher than a predefined threshold. Needless to mention that there are certain solutions which are already existing and are open source. Novelty is a key aspect, and the solutions which are novel in terms of architecture and the solution proposed will be considered. That was all for problem statement 5. In case of any support or any other queries, please feel free to write to us at support@armbharatchallenge.com. Thank you.